100 facts about semiconductors. Basic concepts. 1. Definition. Semiconductors are materials with electrical conductivity between that of a conductor and an insulator. 2. Common materials. Silicon, germanium, gallium arsenide, and silicon carbide are common semiconductor materials. 3. Doping. The process of intentionally adding impurities to a semiconductor to control its electrical conductivity. 4. P-type and N-type. Semiconductors can be doped to create P-type, positive charge carriers, or N-type, negative charge carriers, materials. 5. Band gap. The energy difference between the valence band and the conduction band in a semiconductor. Applications. 6. Transistors. The fundamental building blocks of modern electronics, enabling amplification and switching. 7. Integrated circuits, ICs, microchips containing millions of transistors and other components. 8. Microprocessors. The brains of computers, responsible for processing information. 9. Memory devices. Store data, including RAM, ROM, and flash memory. 10. Diodes. Allow current to flow in one direction only. 11. LEDs. Light-emitting diodes used for lighting and displays. 12. Solar cells. Convert sunlight into electricity. 13. Sensors. Detect various physical quantities like temperature, pressure, and light. 14. Automotive electronics. Control systems, entertainment, and safety features in cars. 15. Consumer electronics. Smartphones, tablets, laptops, TVs, and gaming consoles. 16. Industrial automation, robotics, control systems, and manufacturing processes. 17. Healthcare, medical imaging, diagnostic equipment, and wearable devices. 18. Telecommunications, networks, modems, and routers. Manufacturing. 19. Wafer fabrication, the process of creating thin slices of semiconductor material. 20. Lithography, using light or electron beams to create patterns on the wafer. 21. Etching, removing unwanted material from the wafer. 22. Deposition, adding layers of materials to the wafer. 23. Implantation, introducing impurities into the wafer. 24. Testing, ensuring the functionality of the finished chips. 25. Packaging, enclosing the chips in protective cases. History and trends. 26. Early semiconductors, point contact diodes and vacuum tubes. 27. Transistor invention, by Bell Labs in 1947. 28. Integrated circuits, pioneered by Jack Kilby and Robert Noyce in the 1950s. 29. Moore's Law, the observation that the number of transistors on a chip doubles approximately every 2 years. 30. Nanotechnology, creating devices at the atomic and molecular scale. 31. Quantum computing, utilizing quantum mechanics for computational tasks. 32. AI and machine learning rely heavily on semiconductor technology. 33. Internet of Things, IoT, requires numerous semiconductor-based devices. 34. 5G and beyond, advanced wireless communication networks. 35. Autonomous vehicles, depend on complex semiconductor systems. Materials and properties. 36. Silicon, the most widely used semiconductor material. 37. Germanium, used in early transistors but less common today. 38. Gallium arsenide, faster switching speeds and higher frequency applications. 39. Silicon carbide, high temperature and high power applications. 40. Diamond, potential for quantum computing and high frequency devices. 41. Band gap engineering, tailoring the band gap of semiconductors for specific applications. 42. Doping levels, controlling the electrical conductivity of semiconductors. 43. Carrier mobility, the ability of charge carriers to move through the material. 44. Resistivity, the resistance of a material to electrical current. 45. Dielectric constant, a measure of a material's ability to store electrical energy. Challenges and future directions. 46. Supply chain issues, global shortages and geopolitical tensions. 47. Manufacturing costs, high costs associated with semiconductor fabrication. 48. Energy consumption. The energy required to manufacture and operate semiconductor devices. 49. Environmental impact. The environmental footprint of semiconductor production. 50. Ethical considerations. Concerns about the use of semiconductors in surveillance and warfare. 51. Emerging materials. Research into new materials for semiconductor applications. 52. Heterogeneous integration. Combining different types of materials and devices on a single chip. 53. 3D integration. Stacking layers of circuitry vertically. 54. Neuromorphic computing. Inspired by the human brain's structure and function. 55. Quantum computing. Overcoming challenges to realize practical quantum computers. Fun facts. 56. First transistor. A point contact transistor made of germanium. 57. Smallest transistor. Measured in nanometers, smaller than a human hair. 58. Fastest computer chips. Operate at gigahertz and terahertz frequencies. 59. Silicon Valley. Named after the abundance of silicon used in semiconductor manufacturing. 60. Semiconductor manufacturing facilities, often referred to as fabs. 61. Clean rooms. Semiconductor manufacturing requires extremely clean environments. 62. Semiconductor industry revenue, billions of dollars annually. 63. Global semiconductor market, dominated by a few major companies. 64. Semiconductor patents, a highly competitive field. 65. Semiconductor research, ongoing efforts to develop new technologies. Additional topics. 66. Semiconductor physics, the underlying principles governing semiconductor behavior. 67. Semiconductor device physics, the study of specific semiconductor devices. 68. Semiconductor circuit design, creating functional circuits using semiconductors. 69. Semiconductor testing and reliability, ensuring the quality and longevity of semiconductor devices. 70. Semiconductor packaging, protecting and connecting semiconductor chips to external circuits. 71. Semiconductor failure analysis, investigating the causes of semiconductor failures. 72. Semiconductor recycling, efforts to recover valuable materials from end-of-life devices. 73. Semiconductor education, training and development of semiconductor engineers. 74. Semiconductor careers, opportunities in research, development, manufacturing, and design. 75. Semiconductor industry organizations, associations and standards bodies. Global semiconductor landscape. 76. Asia, the dominant region for semiconductor manufacturing, led by Taiwan, South Korea, and China. 77. United States, a major player in semiconductor design and research. 78. Europe, focuses on niche markets and research. 79. Japan, strong in memory devices and materials. 80. Emerging markets, increasing semiconductor production and consumption. Semiconductor and society. 81. Economic impact, semiconductors drive economic growth and innovation. 82. Technological advancements, enabling breakthroughs in various fields. 83. Quality of life, improving living standards through technological advancements. 84. Global connectivity, facilitating communication and information sharing. 85. National security, critical for defense and intelligence. Semiconductor industry trends. 86. Consolidation, mergers and acquisitions among semiconductor companies. 87. Vertical integration, companies controlling multiple stages of the semiconductor supply chain. 88. Outsourcing, reliance on contract manufacturers. 89. Intellectual property, protection of semiconductor designs and technologies. 90. Government policies, government support for semiconductor industries. Future outlook. 91. Continued growth, the semiconductor industry is expected to expand in the coming years. 92. New applications, emerging markets and technologies will drive demand. 93. Technological challenges, addressing limitations and developing new solutions. 94. Sustainability, focus on reducing environmental impact. 95. Global competition, intense competition among countries and companies. Additional resources. 96. Semiconductor Industry Association, SIA, link to